So share screen. Perfect. So, yes, what we started last time was talking on random walks and expanders. And I'm just going to remind you what we did last time and sort of, the definitions and everything. Then I'm going to, that will be our main topic for today, understanding random walks and expanders. So just to remind you, before we start with the formal definition, the informal sort of picture you should have in your mind that you have this big graph, and there's some edges here, right? So it's and you do some random walk. So at some point you're at some node, maybe here, and then you take a step. So maybe you take a step and you walk, I don't know, here. So you choose one of your neighbors uniformly at random, and you just go there, right? So and then you just keep doing that, right? So keep walking and walking, and maybe you come back at some point. I mean, so it's fine. Now you can define these random walks for like non-regular graphs, and it's fine. It doesn't make sense to do it in some cases, but for us, we're just going to focus on regular graphs because it just makes everything easier to describe. Like for example, at every point, you only have exactly the same number of nodes coming out, and what's called the stationary distribution that we discussed last time. The distribution you're going to get at the very end, if you do it many, many times, it's just going to be uniform on all the nodes. So let me just remind you of the definitions and also see why we're using this normalized adjusted symmetry, so it's convenient for analyzing things. So just a reminder from last time. So we're going to have G, which is DE, which is the regular graph. Look at the normalized adjacency matrix. So this matrix whose value of coordinates UV is either 1 over D if UV is an edge, or it's 0 if not, otherwise. Right, it's not an edge. And we said that the benefit of looking or working with this adjacency normalized matrix is because it gives us a very convenient way of asking, given currently some distribution over the nodes, if I take a single step in this random walk, what's going to be the next distribution? So let me remind you of that. So again, here's another. So we're going to work with distributions. So I'm going to use pi to denote distribution over the nodes. And somebody was asking, do I think of it as a distribution or as a random variable? And it doesn't really make a difference. I mean, I really got to ask, it's probably more convenient to think of it as a distribution, as a sequence of numbers given for every node, what's the probability you're going to be there at a specific point in time. So we can view this as basically, maybe a vector, maybe pi v1, pi vn, and we can view it either as a vector in RV or as a function from V to R, and they're both equivalent, but in some cases one is going to be more convenient than the other one. And the question that we were discussing last time is the following question: if a node, okay, if we choose V and V according to some distribution pi, and take a step and take a single random step, then go to a random neighbor, what will be distribution of the say target node. Right, so we asked this question last time. So again, we'll start with some arbitrary distribution of the nodes. So we choose a node according to the distribution. Then we go to a random neighbor. What's going to be the target distribution? And we saw the answer. The answer is just going to be AG pi. Right, so it's very simple. If I'm giving you a distribution and just write as a vector, multiplied by this matrix, the normalized adjacency matrix, that's going to give another vector, which is going to be the new distribution. And let me just remind you why this is true, because what is AG pi at some node U? Well, by definition, 1 over D, the sum over all V, which are, no, I'm just plugging in the definition of AG. All the neighbors V of U, right, of pi V. Which is exactly the same as saying, well, how can I reach to node U? I need to start from a neighbor of it, some neighbor V. The probability I reach pi V, I was at pi V before, so I was at V before is pi V, and then taking one random step, I'm going to reach this node U. And notice here we're using the fact that both U and V have degree D, right? This is what we also implicitly assuming it here. Because I want to say, well, the probability from V I'm going to reach U is 1 over D, and also from U I'm going to reach V is 1 over D. Now, if the graph is not regular, this is not true anymore, and then we need to define this normalized adjacency matrix in a slightly different way, which is somewhat more annoying, but you can still do it, everything would work. But for us, it's simpler, assuming that the graph is regular. Okay, so this is basically where we stopped last time, more or less. And so first, let me see if there are any questions on that before we'll start discussing properties of this random box. No. So let me also remind you, so also just applying recursively. So after taking T steps, the distribution is going to be AG to the T pi, right? Just by induction. So taking a high power of AG corresponds to taking many steps in this expander. And now let's make a new definition, which is going to be mixing. So this is just a recap of what we did last time. So now we're going to start something new. And that's going to be the definition of mixing, or mixing time. Try to adhere to the notes. So that's the definition. So let G be a graph. Choose some L epsilon. So define T of G and epsilon. That's going to be the mixing time of G up to L epsilon to be the minimal T such that the following holds. For any initial distribution by init. So we take these steps and get distribution pi t, and we require that we look on pi t and its L1 distance to the uniform distribution, which I'm just going to use pi s for this stationary distribution. So let me remind you a few things about this definition from last time. So first of all, let me put it here on the side. So pi s was a stationary distribution, meaning it's a distribution over nodes, but if I take a single step, I'm going to stay at the same distribution. And we said that if G is regular and connected, then pi s is just a uniform. That's the only possible stationary distribution. So if I'm at a completely uniform node and I take a single step, I'm still going to be at a completely uniform node. Okay, that was one comment. And the second comment was about this L1 difference of distributions, that we said that it is essentially the same as this total variation distance of distributions up to a factor of 2. Okay, so if you ask why use L1, because L1 is equivalent to the total variation distance, which is to some extent the largest possible distance, because it sort of measures any possible event that might try to distinguish these two distributions. So again, let me just remind you, or maybe just a recap. So that the total variation distance between two distributions, pi1 and pi2, is the maximum of all possible events. This event happens under pi1 minus under pi2, so we're trying to distinguish these two distributions. And we said there was this claim, but it didn't prove it. It's a simple claim to verify. This just equals up to a factor of 2, the L1 distance. So we care about factors of 2 here, so we're just going to use L1 instead. Okay, so going back to this definition of mixing time. So what we're saying here is T is such a number such that it doesn't matter where we start. Like you can imagine starting at a specific node, right? Maybe without any randomness. We take T steps, we're super close to uniform, right? And so this pi s, it's just the uniform distribution. So we get very close to uniform. And the question is, well, for which graphs can we prove that they mix fast? Okay, what's the best you could hope to mix? Definitely if the graph has some diameter, let's say delta, then there are two nodes whose distance is delta. They're just going from one to the other without even any randomness. You need delta steps. So ideally, what we would like is to mix in time that is proportional to the diameter of the graph. That's the best we could hope for. And expanders exactly give us that. So now I want to prove this lemma that gives us exactly that. So here's going to be the lemma that we're going to prove. So if G is a lambda expander on n nodes, then this mixing time up to getting error epsilon in L1 is at most the following quantity. So it's going to be log square root n over epsilon over log 1 over lambda. Okay, so before we show the proof, let's understand these parameters. So if you're thinking of lambda as a constant, then the denominator is just a constant. And of course, we need lambda to be bounded away from 1, because if lambda is 1, we divide by log 0, which is infinity, right? So we divide by 0. So to get a denominator to be some constant that is bounded away from 0, we need lambda to be bounded away from 1, which is exactly the property we want for an expander. What about the numerator? So remember that log n is basically the diameter. If I have a constant degree graph, its diameter is something like log n. Can't be less than log n. So the numerator up to this factor of epsilon is the best you can hope to get. I mean, ignore these roots and everything. We see in the log they're just constants. So basically, and also you can show that epsilon is the best you can get. So to some extent, this is the best you can hope to get, maybe up to constants. And this is true for an expander. Okay. So let's prove this now. But before proving, are there any questions on the statement of this lemma? So the proof is going to use linear algebra, which is what we're always using, because we assume spectral expansion, which is a linear algebraic property. By the way, whenever I'm going to write lambda expander from now on, I'll just mean lambda spectral expander. So I want to write spectral expander from now on, I just assume implicitly we mean spectral expansion. So the trick is to, although we care, so fix some distribution. Let's call it maybe pi 0, some initial distribution. And fix t. Let t be determined later. and we're going to get the bound that we're claiming to get. So our goal is to prove that AG by 0 to the t minus, and now I can just going to say uniform U. So U is going to stand for the uniform distribution in L1 is at most epsilon, right? That's our goal. Doesn't matter where we start, which initial distribution, we're going to get L1 epsilon. But the trick will be not to directly study the L1 distribution. Instead, we're going to study the L2 distance. So we're going to also work in L2 because L2 behaves much nicer with linear algebra. So we're working in an inner product space. And only at the very end, we're going to convert from L2 guarantees to L1 guarantees. Okay, so that's going to be the main trick. So let's first see what can we say about. So initially, we're going to prove bounds in L2 and then convert to L1. So let's first ask, what would a single step do to the L2? So let's again choose some. So let's say pi be some distribution, maybe pi 0, maybe something we get after some steps. And let's look on AG pi minus uniform in L2 now. So I'm asking, and I want to compare this to pi minus u in L2. Because I want to ask, I have initially some distribution pi that has some distance from uniform, but I'm using the L2 distance to measure it, not L1. I really care about L1, but I'm using L2 as a proxy. And I'm taking a single step with my expander. How does it contract the L2 norm? Okay, that's going to be the first thing we're going to try and understand. So let me just write this as AG pi minus u. Why? So here I'm using the fact that AG of u equals u, right? U is a stationary distribution. It is an eigenvector of AG with eigenvalue 1. So u is the same as AGU, right? And now I want to argue that pi minus u is a vector that's orthogonal to 1. Why? Well, if I have pi as a distribution, it sums to 1. U is another distribution, sums to 1. Their difference sums to 0. So the difference is orthogonal to the all 1 vector. So now we can exactly use this definition of expansion, saying that any vector orthogonal to the all 1 vector has is hit by eigenvalues that are very, very small, at most lambda. So it shrinks by a factor of lambda. That's going to be less than lambda times the L2 norm of pi minus u. Okay, so that's a main step here. Let me just see if I can. I don't know if there's a way to move stuff around here. Let me see if I can play with notability. This is one thing you can do in a physical world. Right. So what did we see? We saw that if we measure distance with respect to L2, taking a single step by an expander shrinks the distance to uniform by a factor of lambda. So of course, if it does it one time, you can ask what if you do it many times. So taking t steps is going to shrink it by a factor of lambda to the t, right? So if I have AG to the t pi minus u in L2. So again, I can write this the same way by AG to the t pi minus u. That's going to shrink by lambda to the t pi minus u L2. Okay. So we get that this shrinks a lot. So now we ask, well, how can we bound this thing? So I'm claiming, first of all, that this is at most lambda to the t. So if I have any distribution pi minus u in L2 is at most 1. So let's see why. So this is because pi minus mu in L2 is at most 1. I mean, let's just do the calculation here. It's a simple calculation. What is pi minus u L2 norm squared with the sum of all v pi v minus 1 over n. Okay, I'm teaching now. I'm teaching now. So what is this here? So it's just going to be the sum of pi v squared and minus actually 1 over n, right? Because the sum of pi v is 1. So we get sum of pi v times 1 over n. We lose minus twice 1 over n, and we get another plus 1 over n. And so, of course, pi v is at most 1. So that's going to be smaller than the sum pi v, which is 1. So just that. So bounded by 1 is actually lossy. So we get the better bound, but it doesn't matter. So it's at most 1. Okay. So now what can we say? Now finally we want to convert back from an L2 estimate to an L1 estimate. And now let's do that. So this here just is Cauchy-Schwarz. So in general, the L1 norm of a vector W, so if W is a vector in Rn, is at most root n, it's L2. And this is just Cauchy-Schwarz. So if you've never seen it, I'll show you quickly why. So what is this? It's just a sum of Wi. So it's the inner product of the vector, absolute value of W with the O1 vector. And by Cauchy-Schwarz, this is smaller than the norm of W, L2, times the norm of the O1 vector, L2, that's root n. Okay, so this is just a simple Cauchy-Schwarz. So we can bound the L1 by root n times the, the L2. And in fact, n is not, it could be the number of, the side of the domain, but it's actually the number of non-zero coefficients. Actually, later on, we're going to see that we can use tricks where if we know W is sparse, we can get even better bounds there. But for now, just the dimension n. Okay, so now let's put it all together. What do we get? Let's see. So we have this AGT pi minus u in L1 is at most root n AG to the power t pi minus u in L2, which we said is at most root n times lambda to the t. Right, so we combine the L1 to L2 conversion and the L2 bound. And now our goal was to get this to be less than epsilon. So what we need t, so that root n lambda to the t is at most epsilon. And if you just solve for this, you get exactly the bound that we claimed, right? So t is going to be log of root n over epsilon over log 1 over lambda. This finishes this proof. So, I mean, I want to see if you have questions, but I want to say that the two things that you want to remember this proof is one, that when you work in L2, calculations are very simple because norms are in L2 and the way we define spectral expansion is in L2. And that we can, in general, if you want to bounce on L1, you can first get bounce on L2 and then convert to L1 by using another root n factor. So these are the two facts I want you to remember about this proof. So now let's see, are there any questions? No, perfect, okay, good. So now I want to show you, so by the way, there is a nice corollary of that you're gonna have in your homework. Or let's say that if G is a lambda expander, then the diameter of G is at most order of log n over log 1 over lambda. If you remember, we saw previously, or we said previously that, you know, if the graph using the expander mixing lemma, we can get the bound of order log n if lambda is bound away from 1. And this says that if lambda is really, really close to 0, you can get a better bound. And actually, it even allows to prove a weak connection between lambda and the degree of the graph, because the diameter of a graph cannot be more than log n divided by log base d of n. So that will give some connection, but we're going to see later a much stronger connection between lambda and d. So again, all of these things are part of your framework, so you can see them there. Perfect. Okay, so now I want to move to a nice application of these things, because now it's going to be something. This will be talking about heating sets. So far, so that's going to be another property in which we want to argue that random walks on expanders mix fast, they behave like no completely random choices of nodes, even though they're not. So what's going to be the idea of a heating set? So there are different ways you can do it. We choose one of them. So we have a graph. So let's draw this graph here. I don't know. Okay, so we have a graph, and we're doing a random walk. And what we're going to ask is the following question. So let's choose a few nodes and call them bed nodes. Maybe these ones are bed. And we're going to ask the following question. Is it likely that a random walk is, let's call this, trapped in a small set of bed nodes? Okay, so the way we think about these bed nodes depends on the application. We'll show one application in a bit about doing error reduction for randomized algorithms, where every node corresponds to a random seed to a randomized algorithm, but that's a very, but we'll see it much more generic. So you have some expander graph, and the nodes correspond to something, some objects, and you want to select a sequence of these objects. And the way you're going to do it is by starting from a uniform object and taking like a random walk in this expander. And that is much more randomness efficient than just shooting them completely at random, one by one. And we're going to ask, well, what's the probability they're all bed? So I don't know what bed is, but not too many nodes are bed. Maybe some constant factor, maybe a third of it. And we're going to ask, well, what's the probability that all this random walk is trapped in this set of bed nodes? And what we're going to prove is that's going to be not a very likely event. I mean, that's going to be unlikely. So let's start to do it a bit more formally, and then we're going to see this application. So again, let G be a graph, and let B be a subset of V, which we're going to think of the bed nodes. So, and it's not too big, so the set of B is something like, let's say, beta. Yeah. So think of beta as maybe a third or something, not too many. And let's define the following property. Think about the following event. So here's the event that we care about. It's going to be the bed event. So we're going to sample V0 in V uniformly. So the first starting node is just random. But then we're going to take a random walk. From V0, so we're going to get, V1 up to Vt for some parameter t. So we're going to start the random node and then take t steps. So it's a t-step random walk. And we're going to find the following probability P. P is going to be the probability that all these nodes, V0, V1, up to Vt, they're all trapped in this bed set of nodes. And our goal will be to show that this is not a very likely event, right? If you take a long enough, of course, maybe the first node happens to be there, and the second and the third, but it's, as I choose T larger and larger, it becomes, you know, harder and harder to stay trapped in a small set. And again, the intuition should be that in a small set, in an expander, if it's an edge expander, there are many edges to go out. So it's not going to be likely never going to take these edges and go out. But the way we're going to prove it is based on spectral expansion, not on edge expansion. So we're going to prove the following theorem. It says, if G is a lambda expander, then this probability Bt is at most beta plus lambda to the T. Okay. So what can we learn from that before we prove the theorem? Let's say beta is a third. We choose lambda to be a small enough constant, like a third. So then we get that this probability is exponentially small. As we choose T larger and larger, it becomes exponentially small. Even though if you think about it, no, we only choose one random node here, just V0. All the rest, we just take a random walk in the expander. And you know what, if the expander is a constant degree expander, every time I have only constantly many options of what to choose. So I use a few random bits. And despite doing that, it qualitatively behaves as if I chose them completely at random. So just compare this before we put it, so compare to the case that if we chose V0 to Vt in V uniformly at random, then the probability would be, right, beta to the T plus 1. Right, because if I choose, again, we have T plus 1 nodes. I want all of them to land in this bed set. So it's going to be beta to the T plus 1. So if you think about it, if beta plus lambda is less than 1, and T is large, those things are roughly the same, right? So we compare here, you know, I guess, what we get in the completely random case and what we get in the pseudo-random case, the case where we just start with one random node, then take a random step, random walk. Now, there are some discrepancies here that I'm going to talk about later, about T versus T plus 1. That's one question. Why do we get different power? And also, what if beta plus lambda is more than 1? Then we get a trivial bound. Can we recover from that? So we're going to talk about both of them after proving the theorem. So both can be addressed, but first let's prove the theorem, because we're going to see most of the ideas coming there already. Okay. So before proving the theorem, is there any question on what we're trying to prove or why it's interesting? So let's prove it. So again, the idea is going to be that you want to use some linear algebraic properties to capture this probability we're trying to compute. So we want to use linear algebra to capture this P, Bt. That's going to be the first step. How do we use linear algebra and the matrices and the vectors to capture that? Well, so first, I need to make one definition. So here's the definition. So define pi b to be the projection operator on B. What do I mean? I mean, it's a matrix. And its VW coordinate is going to be the following. It's going to be either 1 or 0. It's 1 if V equals to W, and they both lie in B, and it's 0 otherwise. Right? So it's just a diagonal matrix, and if it has 1 in the set corresponding to B, and 0 otherwise. So that's a projection matrix. So if I take a vector and I multiply by pi b, it basically erases all the coordinates outside B. So now let's see. What is this PBT? So let's write this PBT. Well, PBT, we said it's going to be the probability that V0, V1, up to Vt all belong to the set B. And I'm going to claim that this equals the following quantity, then I'll explain why. So I take pi b ag t pi b L1. Okay. So for now, maybe it's not clear why it's this quantity, but I'll explain it in a minute. But I just want to show you that there is a way of using linear algebra to capture exactly what we're trying to capture. So now let's see why. So imagine tracking, all of this, all these probabilities. So we have U. So we start with V0, which comes from this distribution U. So pi BU is exactly the probability. So what is pi BU? So we start with U. U is just going to be 1 over n, 1 over n. So first I want to require V0 to be in the set B. So I want to say if we start every node, any node that is not in B, you fail, right? So we get pi BU, which is just this distribution where we just say, well, let's say the first ones are B and the rest one are not. So it's going to be 1, same thing, and then 0, right? So we just erase all the coordinates outside B, and this just comes to capture the fact that we want V0 to be in. Well, if I take this, so that's going to be it's not a distribution, it's a sub-distribution because there's some probability of failing, right? So it's some probability that still survive. So just requiring V0 to be in B. Now we take one random step. So this is for V0. For V1, what do we do? So we take this vector and we look on AG pi B U. That's going to be saying, well, if you survive the first step, what's going to be the probabilities in the next step, right, of V1? And also I want this to be in B. So I also want to also here zero out all the probabilities that are not in B. So formally what we say, so this in coordinate V is going to be the probability that V0 and V1 are in B, and that V1 is equal to B. So this pi B is basically kills all these events of V0 and V1 not being in B, and then we just get this vector, and the V coordinate is a probability of simile. Notice here this does not sum to 1 because we also look on the probability that V0 and V1 are in B. If we sum it up, so if we sum it up, the all V pi B Ag pi B U V, that's exactly going to be the probability of V0 and V1 being in B. And this is exactly the L1, right? Because this is just the vector of probability, just pi B Ag pi B U L1. You see, for t equal to 1, we exactly get this quantity, pi B Ag pi B U in L1 is equal to the sum of all nodes V of this vector pi B Ag pi B U at coordinate V, which is exactly the probability they start at B. So this first pi B here doesn't kill me, stays the same. I take a random walk and again gets to B. So this also doesn't kill me. And then just continue exactly the same way. If you look on t equal to 2, then pi B Ag pi B Ag pi B U L1 is exactly the probability that V0, V1, and V2 are in B, and so I know this might be a bit hard to parse, so maybe take like few 10-20 seconds, think about it, and see if you have any questions on that. Because once we establish that, then we just move to do linear algebra, which we know how to do. So usually the hardest part is converting the quantity we actually try to estimate by some linear algebraic property. Okay. So also in the note, we try to explain it, but I think usually the best way to understand is just to go through it yourself and do the calculations and see why this gives you what we're trying to get. So let's take it on faith now and then see how can we simplify it again. So we have this probability we're trying to estimate. We express as this linear algebraic quantity. And now we're going to try and simplify it and use it. So the first step is going to be just making a change here that's going to be equivalent, but make it easier to analyze. I'm claiming that it's the same when pi b, ag, pi b, t. And then here, pi b. One second. Okay, so why is this true? Well, basically this follows because why? See why? Why does this is the same? Well, the reason is because pi b squared. Pi b squared is pi b. So because pi b the projection operator, just diagonal with ones at some coordinates and zero other places. If you square it, you get the same thing, just project to b again. So if you expand it out, well, always you get pi b, ag, pi b, ag, pi b, ag, and so on. And then you get pi b, ag, pi b, pi b, ag. So sometimes you get two pi b's and not a single one, but they're the same, like pi b squared is minus pi b. And why do we do it? Well, basically because pi b, ag, pi b is a symmetric matrix. So it's going to be easier to work with symmetric matrices compared to pi b, ag, which is not a symmetric matrix. Okay, so again, there's a small technical trick that's going to be useful for us. And now I want to make the following claim. I want to look at this matrix, pi b, ag, pi b, and see how it behaves on vectors. And again, we care about the L1 norm, but we're going to do all the analysis in the L2 norm because it's going to be more amenable to linear algebra. Okay, so get it in different colors in green here. So here's going to be a claim. For every vector, let's call it maybe v, f, I don't know. For every vector of f in Rn, if I look on pi b, ag, pi b, f in the L2 norm, smaller than beta plus lambda f L2 norm. Okay, that's going to be the next main technical part. So this matrix pi projection to b, taken in a random step, and projection to b again, contracts any vector in the L2 norm. So notice here, we're not assuming f is orthogonal to 1 or not orthogonal to 1, any vector gets contracts here. So in particular, this would allow us to prove that this pi b pbt becomes exponentially small very fast. Okay. So before we prove this claim, let me show you why proving this claim will be enough for us. And then we're going to back to proving this claim. So let's again look on this PBT using this claim. But we said it's going to be pi b ag pi b to the t over this vector pi b in L1. We already said that we know how to convert L1 to L2. We just do the root and factor, right? So it's going to be the same thing in L2. Right, it's converted L1 to L2. And now we're going to use this claim. So by the claim, beta plus lambda to the t, the L2 norm, pi b. Okay, and actually here, we're just going to say, well, what is this? Well, I'm claiming, let's just do this last part here. This is smaller than the L2 norm of u, right? Because we just delete some coordinates in pi b, and by u is just uniform, so it's L2 norm is just 1 over root n. It's a vectoring of all the 1 over n coordinates. So this 1 over root n exactly cancels this root n, and we get exactly the bound that we want, beta plus lambda to the t. Okay. So once we prove this claim, we're done with proving the theorem. So modulo proving this claim, are there any questions? So again, this claim was the main tool we use to construct the L2 norm, and then we convert that from L1 to L2, and we present PBT as this L1 of this vector. So now let's talk about proving this claim. Okay. So again, now I want to prove this claim. Okay. So now I want to go back to green. So I want to prove claim. Just to remind you, it said that pi b, ag, pi b, any vector f, L2 contracts. Now, if you remember for ag, what do we know for ag? Well, we know that it contracts only vectors orthogonal to 1. But f could be anything, and pi b f could be anything. So it makes sense to decompose it. That's going to be a new trick. We're going to see taking vectors and decomposing them into some parts that are orthogonal to 1, and some parts which is going to be the rest. There will be some multiple of the constant vector. Yeah, wait 1 second. Okay, so let's see. So I want to prove that. So first step is that we can assume without loss of generality that f is supported on B. So f is 0 outside B. Why? If it's not 0 outside B, then pi bf is going to kill all the parts outside B, so we're going to get like a weaker bound. So we might as well to begin with just erase all the coordinates outside B in this, right? We're going to get the same quantity on the left-hand side and a smaller quantity on the right-hand side. So let's assume that. So in particular, this means that pi bf is just f. Okay, so we can do that. That's the first step. So this is, now I want to say, well, second step is we want to study AGF. Now we know that AG contracts vectors orthogonal to 1. So I'm going to write f as a sum of two things. F is some distribution. Let's assume here also f is a distribution here. So assume that the sum of fd is 1. Because we can normalize by it, so why not? So let's assume that also. And let's write f as a uniform distribution plus the rest. I'm going to call z. So here what we say is we decompose this vector of this distribution, or in general this vector that sums to 1. Actually, it doesn't have to be. I mean, in our case, it's all distributions, but this claim is true even more generally. Even this vector is not distributions, I think. So we'll see. But anyways, we only need two distributions. So we're going to decompose this distribution as the uniform distribution plus the difference. So z is just f minus u. And the whole point here is that z is going to be orthogonal to 1, right? So we can, and then we're going to study what can we say about AG f. Well, we know it's going to be AG u plus z. AG u is an eigenvector of AG with eigenvalue 1. It's just going to be u plus AG. And then we're going to ask, what can we say about, well, the norm of pi b AGF in L2? Well, by triangle coordinates, it's more the norm pi bu plus the norm pi b AG z, right? Just using the two parts. But what can we say about each one individually? Let's see. What is pi bu? Pi bu, let's write it here. Pi bu is just a specific vector, right? In B, we're going to get the value 1 over n. And the rest we're going to get 0. So what's the L2 norm? What's the L2 norm of this vector? Well, it's just going to be, so we have B has size beta n. So we have beta n coordinates of value 1 over n. So we have let's see if I can do the calculation here on the fly. So it's going to be I think what we get here is something like root beta over n. So if I didn't know correct what I'm doing here. Yeah, root beta over n. So that's root beta over n, just by direct calculation. What about the second part? Well, we know that AG is going to contract Z, right? Because Z is orthogonal to 1, and G is the lambda spectral expander. We don't know what pi b is going to do to it, so we're just going to ignore it. So this is at most the L2 norm of AGZ, because pi b just erases coordinates, so it's just going to decrease the L2 norm. And we know because the spectral expander was lambda times the L2 norm of Z, right? So now we need to somehow put all of these things together. So what have we got so far? So we try to get this beta plus lambda L2 norm of F. So far, what have we proven? We've proven that pi b AG pi b F is more than two quantities, root beta over n plus lambda L2 norm of Z. And now we sort of want to connect these two things together. But let me first see, just consult the notes for a second. So remember, in our goal, what was our goal? Our goal was to get beta plus lambda L2 norm of F. Right, that was our goal. And we got something. Not quite what we wanted, but something. So Clement, first of all, let's see what we have. So this first part, lambda Z, I claim it's good because this would actually give me this lambda F because, think about it, Z and U are orthogonal to each other. So we know that the norm of F squared is the norm of U squared plus the norm of Z squared. But F is U plus Z and U and Z are orthogonal. So in particular, the norm of Z is smaller than the norm of F. So this would give me the first term, right? So this lambda norm of F, we're done, like we have it here. So now we just need to worry about the second part. So somehow I want to relate root beta over n to the norm of F. And here we're going to use this assumption we had that F was supported on B also. So what can we say about the norm of F? Remember, F, we assume without a lot of generality that F is supported on B. So what is the L2 norm of F? So again, so what is this? We can say it's a sum over all B in B, FV square, let's do 0 square. Sorry, let me do it in a slightly different way actually. Easier to do it the other way around. Let's look on the L1 norm of F. But F is a distribution, so this is just one. So this is a sum over all V in B, FV. So now we're again going to do Cauchy-Schwarz, but now we're only because it's supported on B, we can say this is smaller than the L2 norm of F times 1 supported on B, L2. Because we know that F is going to be 0 outside B. And what is this 1 on B and 0 elsewhere? Well, that's exactly going to be root beta n. So this is 1 on B, 0 elsewhere. What are the questions in the chat here? Okay, Max responded. So now if we just put all of this together, what did we get? So we got that the L2 norm of F is greater than 1 over root beta n, right? Or another way of saying that if you look at this root beta over n is smaller then beta, well, it's equal to beta times 1 over root beta n, which is smaller than beta, the L2 norm of F. Okay? So there was a bit of a circumvent way, but we said because F was supported on B, the second error term we got here, this one, we can directly say this is smaller than beta, the L2 norm of F, because F is supported on B, and because F is a distribution. Okay. So again, I think if this is not clear, probably the best thing is just, I mean, you go through the notes, we have the same calculation there, and maybe it's easier if you read on your own, but what I want you to remember is that what we did here, the main thing we did here is, first we expressed this quantity we cared about, this PBT, by this L1 of this vector. We bound the L1 by the L2. For the L2, we proved that this operated pi b, ag pi b contracts any vector by beta plus lambda. And then we proved it by doing this analysis. So we decomposed F into the part that is orthogonal to the one vector Z and the plus uniform. And we analyzed each one separately. Okay. So even if something is not completely clear at this point, I mean, you can probably check it later or ask later, but that's somehow was the main contracting claim, this claim here. And once we have that, everything else follows. So why does this claim make sense? We say you first restrict to being in a bad set B, small set. You take a random walk and you want to still stay in this random small set. This should not be super likely because this is an expander, right? So this doesn't explain when we get this specific bound of beta plus lambda, but it explains why we should get some bounds. Okay. So let me make a couple of claims on this theorem. So the bound that we got was this probability is at most beta plus lambda to the t, and we compare this to the case of choosing v0 to vt completely random uniformly, which gives beta to the t plus 1. So I want to now talk about two aspects here. One is sort of t versus t plus 1. We make t steps where we see t plus 1 nodes. Why should we get some to the power t and not some to the power t plus 1? Well, the answer is just because our analysis was a bit sort of, not too tight. So there is a way of refining it. So one, I want to argue that this, so you can get this better bound where you have another factor of beta here. Okay, so there's actually there's a paper showing that, and in fact this is tight. So this is in fact, even show the other side is at least beta minus 2t, minus 2 lambda, sorry, the t. So up to this plus or minus 2 lambda, that's the right answer. And this is, again, if lambda is 0, this gives again beta to the t plus 1, and not beta to the t. So that's one comment. And the second one says, well, what if beta and lambda are both below 1, but the sum is more than 1? Let's say beta is 2/3 and lambda is 2/3. Conceptually, this is still an expander, and beta is still small. We still expect an exponential decay, but this specific theorem doesn't give us that, because beta plus lambda is more than 1, so we get a trivial bound on a probability, more than 1. So the second thing, this can be improved to the following better quantity. That says, well, as long as lambda is below 1 and beta is below 1, even if they're both 0.9, you still get an untrivial bound. And that's actually going to be part of your homework. This is one of the questions in your homework, is to improve the analysis of the theorem and get this bound. So you need to think in what places the analysis is not sharp and how can you refine it. Okay, so that's going to be your second task in the homework. Now, the last thing I want to show you today in our remaining 15 minutes is a nice application of these things. And the application is going to be for error reduction in randomized algorithms. Okay, so what is a randomized algorithm? It's an algorithm that takes an input and also uses randomness to try and compute a solution. And let's just focus on decision problems for concreteness. Meaning that my algorithm takes an input X, and I'm also going to assume it takes a randomness as a second or auxiliary input. So instead of the algorithm generating randomness on the fly, you can equivalently just provide all the randomness it needs ahead of time. So just a secondary input. And this is going to answer, it's going to answer yes or no. So there's going to be some answer in, let's say, yes or no. And so we say that A computes some function f of x with error epsilon. Let's say with error, let's say 1/3 for concreteness. Or let's say epsilon. Error epsilon. If, well, there are two notions. There's the one-sided and two-sided notion. So the two-sided notion, let's say weaker notion, it says that for every x, the probability of a randomness AXR equals fx with at least 1 minus epsilon. So this is the most standard notion of randomized algorithms. For every input x, there is no randomness over the inputs. For every input x, the algorithm provides the right answer with high probability over the what? Over the internal randomness of the algorithm. Except that now we're providing external. There's also a one-sided notion that said, well, one of the answers there's no error. So if f of x, for example, if f of x is 0, then AXR is 0 for all r. But if f of x is 1, then the probability over r AXR is 1 is at least 1 minus epsilon. Okay. Now, what I want to show you is how we can reduce the error in randomized algorithms or not paying too much in extra randomness. So assume A is a one-sided error, let's say 1/3 for concreteness. And it uses some number, let's say m random bits, some number m of random bits. And our goal will be to reduce the error to some tiny epsilon. How can we do it? Well, here's one way, that's simple way. So here's a simple way. We're gonna randomly choose random strings. So let's say R1 up to RT in 0, 1 to the m. Right? We're gonna run all A X Ri. We know that if ever it says 1, the answer must be 1. Otherwise, so if one of them outputs 1, then return 1, else return 0. Right? So if at least one of them returns 1, then we're going to say 1, and if all of them return 0, we're going to return 0. So why is it a good way of reducing error? Because we're assuming a one-sided error, right? So if f of x is 0, all of these algorithms are going to return 0 all the time. So we're going to return 0, right? So on the other hand, if f of x is 1, then each one of them is going to return the correct answer with 2/3. So the probability of an error here, so let's see, so if f of x is 0, we return 0 always. That's good. F of x is 1. We return 1 with probability. Well, the point that we make a mistake in each step is a third. And we make a mistake in all of them. So it's going to be 1 minus third to the t. Right, so the error that we get is 1/3 to the t, exponential in t, and the number of random bits we need also scales with t. It's going to be m times t, right? Because we just generate t independent sequences of random bits, right? So far we haven't used expanders in any way. We just repeated this randomized algorithm several times and just use all the answers to produce the results. So next we're going to see how to do better using expander graphs. But before that, are there any questions so far? Okay, so how can we use expander graphs? So here's going to be a cool application. So let G be a lambda expander where the nodes I'm going to think of them as being 0, 1 to the m. So I'm identifying the nodes of this expander by all possible values of these random strings that this algorithm might take. And instead of sampling them independently, I'm going to sample them by a random walk. So let's sample V0 up to Vt in V by a random walk. And again, I'm going to think maybe, for example, lambda is to be a third, and my degree is going to be some constant. Let's assume that for a second. Some constant degree expander with lambda being a third. So what's the number of, we'll analyze this in a second, why it's still going to work. Notice now, only the first node is completely random. All the rest are generated by just taking a step from it. So they're not random at all. So what's the number of random bits we use here? Well, the first node is completely random. We're going to use m. But all the rest, all the other t of them, just going to be basically log d. Right? Because every time given a node, I need to choose one of its random neighbors, only d options. And we need log d bits to specify this neighbor. D is a constant, so it's m plus order t. Notice the difference. Here we have m plus t. Before we had m times t. So we only pay additively in how we want to reduce the error, not exponentially. And my claim is going to be that also here, epsilon is going to be something like 2 to the minus order t. Exponential in t. So it behaves the same, but instead of paying m times t random bits, we pay m plus t, or m plus a constant times t random bits. It's much more randomness efficient. So let's prove this claim. This is going to be a simple application of our theorem from before. So again, we have this graph G. So here's a graph G, where every node corresponds to a particular sum value of these random strings. So let's fix x. And what we want to analyze is the probability that we make a mistake. Probability that the algorithm makes a mistake on x. So what's the algorithm? Well, it's exactly the same algorithm as before. You run exactly this simple algorithm. The only difference is that we don't generate these random strings one independently, uniformly. We just the first one randomly and all the rest ones by a random walk. But then it's exactly the same algorithm. If one of them outputs 1, we output 1. Otherwise, we output 0. Okay, exactly the same algorithm. So I won't write it again. What's the analysis? So this was the analysis from before. And then we can just repeat this analysis again. Well, let's see. If f of x is 0, then for every random string, AXR is going to output 0. So we output 0, right? There is There is no option of outputting 1 because we assume this algorithm A always outputs 0 on any possible random string. That's the easy case. So the interesting case is if f of x is 1. And now I want to use our theorem, so we need to define a bed set. So define B to be all these random strings where AX are output 0. So the wrong answer. That's going to be a bed set of random seeds for our algorithm. So by assumption, we know that B is at most B over 3. Why? Because we're assuming this algorithm makes a mistake with probability at most a third. So I don't know what B is. It depends on X. Notice B depends on X, right? I don't know what it is, but I know it's small. So the beta we saw before is a third, or at most a third, right? It's the density of B. So by theorem, so the probability of a mistake is exactly this, what we analyzed before, PBT. It's exactly the probability in this t-step random walk. All of the seeds we choose happen to land in this bed set of seeds where we're making a mistake. And we said that at most beta plus lambda to the t. Now beta is a third, lambda with him is a third, so it's most 2/3 to the t. So again, we get exponential decay of error. So we need t to be, in both cases, we need t to be log 1 over epsilon, or order. Like in both cases, we need t to be order log 1 over epsilon, right? In both cases. Maybe with a different constants here for the O. And the difference is that in the naive randomness or error reduction, we pay times t, the number of randomness we need. But in this sort of more sophisticated way, using expander graphs, we pay plus t, right? So we save a lot. So it's a very simple application. We just use this theorem, as a black box. But I want to show you that it's very interesting that you can think about graphs as representing other objects, not necessarily some arbitrary. Like here, it's represent random seeds, and the edges are meaningless, right? The edges are that we put on them just that we can sample from them efficiently. So the edges don't have any inherent meaning except that they allow us to sample fast from this graph. So are there any questions on this application? So maybe let me say one thing before we finish. So notice here, for example, one thing we needed is to actually not just say there exist expander graphs, but actually to have an efficient way of using them or explicit constructions of them, right? So we need some way of saying there is an explicit graph on 2 to the m nodes, such that given that I'm currently at a specific node, it's easy to find all of my neighbors, and then I can just choose one of them randomly, right? So what did we need? So what did we need? Let's just write it. So we needed explicit expanders. But more specifically, what we needed, if V was 0, 1 to the m, let's say. So what we wanted is, given a node V in V, we can compute its neighbors, constant number of them, efficiently. So let's say in time, let's say poly m, right? Polynomial in the length of the description of the node. So such graphs we actually call strongly explicit. So strongly explicit means that we can, for every node, compute its neighbors in time polynomial in the description, in the bit description of this node, so polylog in the graph size. So if my graph has n nodes, so we run in time, so the runtime is polylog n. So, but again, we're not trying to specify the whole adjacent symmetrics, just a specific row, right? So you can imagine I give you a row, it has a few ones, give me the output, the location of the ones in it, right? There is a weaker notion called explicit that says run in time. So this is strong explicit. Explicit is a weaker notion that says that in time poly-n generate G. So just write out the full adjacency matrix in time, polynomial n, and we cannot do better because the size is poly-n, right? So just to write it out, it has like poly-n, nodes, edges. You can do better. But the strongly explicit might be a bit sort of subtle notion, but it's very important. It says, given the description of a node, I don't care about all the nodes, just give me its neighbors. I want to do that super fast. Polylog n. So the questions we're going to try to understand later on in this class are, do we have constructions that are either explicit or strongly explicit? Okay, that's going to be a notion that will come up when we discuss in week 5 when we discuss constructions. And actually, both constructions we're going to see there are going to be strongly explicit, if I remember correctly. Okay. So maybe now is a good time to stop for today. Yeah, I'll take questions in a second. I'll just say one thing. So what we're going to start discussing starting next week is going to be different applications of expanders in computer science. We're going to see 2 different applications. I mean, there are many. We're going to see 2 of them. One is going to be how they relate to trying to prove lower bounds for linear algebra. And the other one is going to be about how can you use them to construct efficient error correcting codes. There were 2 different applications, both in expanders in different but very interesting ways. That's going to be next week. So now, are there any questions?
I had a question. So we saw an application where the randomized algorithm had a one-sided error. Can this be extended to 2-sided errors?
Okay,
because
great question.
More than hitting sets, we need sort of like a frequency argument of sorts, maybe.
Yes, exactly. Actually, that's one of the questions in the homework, to do that. So what you will need to show there is essentially that if the set of bed set is really small, you take a random walk, then most of the nodes there avoid this small set. Or more concretely, is that if B is a set of nodes, density beta, and I take a random walk, then with high probability, we get something like beta T nodes in the random walk land in B, right? So what we analyzed today was this question of what's the probability all of them land in this bed set. We said it's exponentially small. But in fact, you can show that the same holds if you ask a weaker question, what's the probability many more than just beta fraction of them land in B? And you can prove this as well. That's going to be one of your challenges for the homework. That's a bit of a challenging question. So I guess if people don't know how to do it, we might give some hints later on in Piazza. But it's good to try to do it yourself first. Yeah, but the same thing would work for 2-sided. We just run this algorithm T times and take the majority. So did this answer your question?
Yeah, this is exactly answering it. Okay, thanks. Yeah.
Any more questions? Okay, I guess not. So I guess we'll see you all next time. Bye, everybody.